Hi, welcome to another video short, and today's topic is continuity, or more specifically the precise mathematical definition of continuous functions. Now, as with the limits, we will discover that continuity is a very important mathematical concept to understand, as many of the subsequent theorems and definitions and conjectures that we use in calculus will depend upon our understanding of the principle of continuity. Now, visually, it's very easy for us to understand and recognize when a function is continuous. For if you can draw the function from beginning to end without lifting up your pencil, then you have a completely continuous function. But if you actually had to move your pencil to a different location to continue drawing your function, that location is a point of discontinuity. I think it's best for me to draw a very simple graph that demonstrates a function that has continuous components and locations where the function is discontinuous. Now, just by looking at the graph, hopefully you'll recognize where those locations with the graph is discontinuous. Now, this location here, obviously the graph is continuous on this segment. Likewise, the middle segment, the graph is continuous. And then finally, in the last segment, the graph is continuous there. But you'll notice that when x equals 1, I had to physically lift up my pencil, and therefore we have a discontinuity. Likewise, when x equals 2, I also had to lift up my pencil, so my graph has another discontinuity at x equals 2. Now, when you're dealing with functions that are continuous, or more specifically functions that have discontinuities, they have different categories of styles of functions that it's worth your while spending some time recognizing. The first style of discontinuity is something called removable discontinuity. Here's an example of this. This is a graph where you actually have a point that's been plucked out of the function and moved to a different location. It's as if I can plug the point back into my function to give myself a continuous function. So this type of graph is called a removable discontinuity. Now, some textbooks will define this type of graph also as a removable discontinuity. It's almost identical, except I don't have a point in my domain. But more precisely, this is really known as a removable singularity. That is, if I don't have that point in my domain, it's a removable singularity. But if I do have a point in my domain, it's known as a removable discontinuity. Some other types of discontinuities to be familiar with. One of them is called a jump. This is a good example of a jump discontinuity. This is where the graph physically jumps. You can see where I've actually lifted up my pencil to continue at some other location. You notice I have two jumps in this graph here. Another type of discontinuity is called an infinite discontinuity. This is where the graph goes to either positive infinity or negative infinity or a combination of both. And the final type of discontinuity that you may encounter, and this one's a bit more rare, this is called an oscillating, or sometimes known as a type of essential discontinuity. This is where when my graph goes to a value, in this example when it goes to x equals 0, the function is moving so rapidly up and down that in fact the limit when I'm approaching my x equals 0 from the left side and the right side don't go to the same location. The value is oscillating so rapidly that there is no limit, and then therefore we have an oscillating or a type of essential discontinuity. Now, it's nice to visualize these things, but we want to look at the precise mathematical definition. So how do we mathematically demonstrate the same things that we see physically? So first thing, we have to define that a function f is continuous at x equals a, where a is every element of my domain. So a function f is continuous at x equals a when the first condition has to be met. That is, I actually have to have a point at a, so f of a is defined. So for every element a in my domain, there is a point, so f of a is defined. Also, the limit as x goes to a of my function f of x exists. Therefore, as x goes to a, my graph goes to a, and where the graph goes to, it goes to the same value. And thirdly, that value that the limit goes to is in fact the same value f of a. So if all three of these conditions are met, then we know that our function is said to be continuous. If any one of those fails, then it is discontinuous at the point where it fails. Now, if you look at these three conditions, really only condition 3 is required because condition 3 requires condition 1 and condition 2. So let's look at some examples to see where visually it's easy to recognize that our graphs are discontinuous, but we'll compare our visual interpretation to the precise mathematical definition and compare the two results. So let's look at the first graph. Visually, you can see right away that that's the point where we have a difficulty. So let's look at this precisely mathematically with our three conditions. So condition 1 says f of a is defined. And we look at a graph, and absolutely I have f of a defined. I got a point on my graph. Condition 2 says the limit as x approaches a from both sides of my function must exist. And likewise, you can see as I approach a on my graph from both sides, I do have a limit. But condition 3 says those two values must be at the same location. And obviously, you can see that my f of a is above my limit, and so my graph fails on the third condition. So it's not a continuous function at a, or x equals a is a point of discontinuity. How about my second graph? Well, visually, again, you can see very easily I have a couple of locations where the graph is discontinuous. So I'll pick this point A here and look at the precise mathematical definition. So the first value that I need to look at is f of a is defined. Yep, sure enough, I've got a point A right there, so f of a is defined. How about my second condition? Second condition says the limit as x approaches a of f of x exists. But you'll notice here that as I approach a from the left side and the right side, my limit goes to different locations, and therefore it fails on condition number 2. And if it fails on condition number 2, it has to fail on condition number 3. So again, this is a non-continuous function, and I have two definitions that collapsed. How about the third? Again, obviously, this is the value of interest. So my first requirement is that f of a is defined, and as you'll notice, I don't even have a point at f of a, so it fails on the first condition, and my limit does not exist. That fails on that one, and obviously then it fails on the third one, and we have a condition where the graph fails on all three values. So mathematically, the three components tell us the same things that what we see visually when we look at our continuous functions. Now, before we finish with continuity, there are some additional theorems that's worthwhile looking at. The first one says, suppose that we have two functions, f and g, and both of them are continuous at a point x equals a. Then the following conditions are also met, and that is the sum of my functions, or the difference of my functions, is also continuous at x equals a. That is, f plus g is continuous at x equals a, and f minus g is also continuous at x equals a. Likewise, the product of the two functions is also continuous at x equals a. And then finally, the quotient of the two functions is continuous at x equals a. That is, f divided by g is also continuous at x equals a. That is, as long as g of a does not equal 0. Another theorem that's very, very useful is that suppose that you have a function g that is continuous at a and another function f that is continuous at g of a, then the composition of these two functions, that is f of g of x, is also continuous at a. This is just, it can be easily said this way: if you have two continuous functions, then the composition of these two continuous functions are continuous. Simple as that. So hopefully this precise mathematical definition of continuity will help you understand the concept of continuous functions in your journey of calculus. Thank you for watching. Bye-bye.